Today we are going to discuss the sigmoid function in machine learning, especially in the context of neural networks. The sigmoid function is also known as the logistic function. From a neural network perspective, it is a type of activation function that converts the real valued input into a value between 0 and 1. Mathematically, it is represented as this. Sigma is commonly used to denote the sigmoid function. If the real valued number is x, then the converted value is e to the power x divided by 1 plus e to the power x. Here e represents Euler's number, which is approximately equal to 2.71828. This sigmoid function is characterized by its S-shaped curve, often referred to as a sigmoid curve. This shape makes it particularly useful for converting raw values such as logits into probabilities, which is why it is often used in the output layer of a binary classification model. There are some key properties of the sigmoid function. The range and the output values are particularly of importance here. The output of the sigmoid function lies between 0 and 1, making it ideal for situations where we need an output that represents a probability. Also, the function is differentiable, which means that the gradients or slope can be calculated at any point on the curve. This property is critical for backpropagation in neural networks. Also, the gradients are smooth, which helps the model learn effectively during training. And another important item is that the function is non-linear, which means it can capture complex patterns in the data when used as an activation function in the hidden layer. Historically, sigmoid was used in hidden layers, but other activation functions like ReLU and leaky ReLU have largely replaced sigmoid in the hidden layers. Now, sigmoid is widely used in the output layer, especially when the problem is binary classification. That makes sense because naturally the sigmoid function can help predict the probability of the positive class in binary classification tasks. This makes it easy to interpret the model's prediction as a probability between 0 and 1. Okay, the sigmoid function in the output layer provides the probability that the label is 1, given that the possible labels are 0 and 1. Let's take a quick look at how this equation is formed. Let's say that x is a large number, so large positive number, so x is in this direction. So in that case, e to the power x will be very large. So in the numerator, you have a very, very large number. And also in the denominator, you have 1 plus very, very large number. So a very large number divided by 1 plus a very large number is almost equal to a very large number divided by a very large number, which is 1. So that is what is happening here. So when x, the input value, x in the sigma function is very large, then practically you will see that the probability is almost 1. Now let's consider the negative side here. If you have a very, very negative number, which is large in the negative side, then what happens? So e to the power minus x, where x is very, very, very large in the negative direction, of course, then e to the power minus x would be 1 divided by e to the power x. So in the numerator itself, you have 1 divided by e to the power x. Now 1 divided by e to the power x would be a very small number, a very, very small number, which is very close to 0. So the numerator becomes very close to 0, and in the denominator you have 1 plus a number which is very close to 0. That makes it 0 divided by 1. So sigma of x becomes 0. So that means in the very, very negative side, as left as you go, the function becomes 0. And that is how this sigmoid function gives you 1 when your input value is very large and 0 when your input value is very negative, large in the negative side. Now what happens if you have a value, x value of 0.0? It becomes 0.5 or half. Now how is that? Consider that x is 0. So e to the power 0 is 1. Anything to the power 0 is 1. And in the denominator you have 1 plus e to the power 0, which is 1 plus 1. Hence you have 1 divided divided by 2. So that makes it half, and that is how when x is 0, the sigmoid function returns you 0.5. For the rest of the numbers, for numbers greater than 0, you have a probability, or you have a number which is greater than 0.5. For all negative numbers, gradually you have probability smaller than 0.5. Of course, the function is not linear, and notice here that in the beginning, in the positive side, the probability sharply increases, and then slowly the rate of change of the probability decays. And also in the left side, that is when x is negative, the probability sharply decreases, and as you go further left, the rate of change in probability, that rate decays as well. That's how it has become an S-shaped curve. So sigmoid curve is S-shaped. Okay, so if you have a neural network, and considering that this particular neural network is solving a binary classification problem, you will have one neuron in the output layer, and you send that raw logit through the sigmoid function. After that, you have a probability. So the raw logit is a real number, but when you send it through the sigmoid function, the final output becomes a probability that varies between 0 and 1. So a very high probability would indicate that the label is 1, and a very low probability would indicate that the label is 0. So you can build your error function based on this probability. Generally, binary cross entropy loss is used for binary classification as the loss function. Okay, there are some limitations of the sigmoid function. One is vanishing gradient problem. As the value of x becomes very large or very small, the gradient of the sigmoid function approaches 0. So what does that necessarily mean? Let's say here, when the x value is very large, notice that with changes of x, the probability does not change much. As a result, the gradient of the sigmoid function approaches 0. That means the change becomes almost 0. So that happens when your input values are large, and also your input values are too small. That means too large in the negative side. This can cause the vanishing gradient problem during backpropagation, especially in deep neural networks. When gradients become very small, the model parameters stop updating effectively, making it difficult for the network to learn. And again, this is one of the reasons why sigmoid functions, even though it's non-linear, is not used in the hidden layers. Also, the sigmoid function leads to a slow convergence due to its shallow gradient in extreme values. This is again another reason of why sigmoid function is not used in the hidden layers, but used widely in the output layer of binary classification, where it is intuitive due to its probabilistic nature. Okay, so let's take a look at how we can code it in PyTorch. Let's say that we have a very simple neural network where we have two input features. Then we have a layer where we have nothing but the output neuron. Of course, you can have more complex hidden layers in between. This output neuron is outputting some logits, and that logit is sent through the sigmoid function, and then you have the probability. Let's implement this one in PyTorch. So here is the coding. So we have a simple neural network. We have layer 1 where we have two inputs. There's two inputs, and we have one neuron in the output. And then we are using nn.sigmoid. We're taking this to a variable named sigmoid. And then what we're doing is, in the forward method, the input comes in. We are sending that input through layer 1, which is this particular variable defined in the constructor. Then whatever layer 1 is outputting, which should be just one value, one logit, which is the output of this particular neuron, that neuron's output is sent through that sigmoid function that we defined in our constructor. And the sigmoid will convert that value to a probability. So we are returning that probability from the forward function. So practically it's just the sigmoid function. Just like in a previous video for the hidden layers, we used ReLU or leaky ReLU. PyTorch has its own sigmoid function. So we are leveraging that sigmoid function in this context. Thank you very much for watching this video. Hope to see you in the next one.